Orgo, folks, and Appa says that today we are going to be covering splitting both normal. So essentially a J value is the frequency by which two hydrogens will split one another. So let's just get right into it and I'll explain what I mean as we go. So vicinal is the most common and you should probably know that just in general. Vicinal just means that they are hydrogens that are on adjacent carbons and the value for this is 7. So that's what normal splitting uses. Geminal is kind of important because we talk about this later in the semester. So keep the term geminal in your mind. That just means they're both on the same carbon. Basically, what I want you guys to know is that if he gives you a chair like this, you just have to know what position is what. So he won't tell you axial, axial. He'll just give you this picture, for example. And you have to remember from Orgo 1, if it's straight up or straight down, it's axial. If it's slanted, it's equatorial. So now let's talk for a moment about what you need to know about complex splitting. So we're going to call this hydrogen B, hydrogen A, and C. And the first thing I want you to notice is that this is sp3 hybridized, sp2, sp2, and sp3. And when we just now talked about the J values, we said that regular old vicinal coupling like this had a J value of 7. That was normal splitting. But when you have two different hybridizations, that is not going to be standard splitting. That's going to be different. You don't have to know what the number is, so don't freak out. You don't have to know these actual values. You just have to be able to look at this and see, okay, this J, which we're going to call JAB, is going to be much different than this J value, which we're going to call JBC. And again, the reason they are not equal is because we have an sp2 splitting an sp3 and an sp2 splitting an sp2. In this case, JAB will not equal JBC. To further explain J values, I'm actually going to take the example or a very similar example to the one we just did, and we're going to draw something called splitting diagrams or tree diagrams. So let us go through and do a normal splitting example first. So when we have the red hydrogens, they will be 1, 2, 3 bond lengths. So all of these blue hydrogens are going to be neighbors. So we will have the regular old n+1 rule. We have 3 neighbors. So the multiplicity will be 4, and this is a quartet. And you might be wondering, what do these things mean? How do we even come up with this? So I've drawn a red line right here, which I'm going to move over a little bit. And that red line symbolizes our hydrogen signal. So this correlates here. And this signal is going to be split in half for every one of these neighbors. Bam, bam, bam. And the J value is going to be the value that it splits by. I used 7 for this one just because that's regular vicinal hydrogens. For these numbers, I'm just going to make them up because it's easier to understand that way and you don't have to know the exact numbers anyway. So just know that while we go along with this. So since all 3 of these hydrogens are exactly the same and they have the same J value, when we split it the second time, you're going to have some overlap in the middle. And we have 3 neighbors, so we're just going to split this once more. You get some more overlap. My drawing is not the best, but it gets the job done. All right, so all of these will have overlap. So take a moment to look. And now I'm going to show you how we get those weird peak shapes. So when we had our regular red hydrogen signal without being split, it would look like this and be called a singlet. And I'm sorry for my dog barking in the background. He's having a day. And so for every one of those lines, we are going to draw a peak. So at this level, we would have 1, 2, and that would be called a doublet. Next one down, you need to realize that when you have overlap, you're going to get a taller peak. So it would be small one, a tall one, and a small one, and we call this a triplet. And last but not least, our answer is actually going to be a small peak, tall peak, tall peak, small peak. And I tried to draw it underneath so you could see what I was talking about. It didn't work very well, but here, I'll draw it again. So it would be like a small peak, tall, tall, and small. But I drew that better over here so you can see it. And that's a quartet. So quartet is our answer, and we have 4 peaks. As you can see, that checks out. This makes sense. Now we are going to do the same thing, but with a complex splitting example. And as I mentioned before, we recognize this as being complex splitting because we have sp2, sp3, sp2. So these are different values. We are going to look at the red hydrogen again. That's going to be our goal. And then we are going to use these blue and green hydrogens as our neighbor because as you can see, 1, 2, 3 bond lengths, 1, 2, 3 bond lengths. In this case, we can no longer use the n+1 rule. This isn't a technical rule that like an actual rule, but something I like to use, what that makes sense to me, is n1 plus 1 times n2 plus 1. And the reason I do it that way is because each of our neighbors are going to count as separate entities for now. So I'm going to call this neighbor 1 and this neighbor 2, just because I like going from left to right. So if we continue with our rule, we have 1 blue neighbor. 1 plus 1 is going to give us 2. And then we have 2 green neighbors. 2 plus 1 is going to give us 3. And I know you guys can do simple math, but I specifically wrote this out for a reason, because when we name this, it's not going to be simple naming. It's going to be called a doublet. And the multiplication symbol is going to translate to an of. And we have a triplet. And for the purposes of this class, it would be just as correct if you said triplet of doublets or doublet of triplets, because it's essentially the same answer either way. And 2 times 3, you guys should know, that's 6. So the multiplicity is 6, and we can call that a doublet of triplets. When we go to make the tree then, this is going to be our original signal right here. Let me try to center it a little bit. All right. So first, I'm going to choose to split it by the blue and then the green. And I'm going to choose to give a larger J value for the blue and a smaller one for the green. Again, I'm just making this up because that's the prettiest and simplest diagram that I can draw for you. And the general point is there. Obviously, every diagram is going to look a little bit different, but this is sufficient for you guys. So the first thing I'm going to do is we have 1 blue neighbor, so we're going to split it 1 time. And we're going to pretend the J value is 10. So the blue hydrogen, split it into 2. And for now, it looks normal, like this. And that is a doublet. Next up, we have green. And the green hydrogens are each going to split it 1 time. So bam, and bam. But now, the green hydrogens are going to have a J value of 5, let's say. And now, in this case, there's no overlap in the middle. So that's the difference between here and here. There's no overlap. So that's going to make our signals look different. We're going to, instead of having a tall peak, we're going to have small, 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 small. Again, it was meant to be like that, but it's fine. I'm going to just draw it again. I'm sorry. I just like to have it Perfect. So instead of being called a triplet or a quartet or whatever, we are going to call it a doublet of doublets. And the reason for that is literally because we have two doublets. Sometimes they're nice with the naming. Next time we split it, each of these are going to split one more time, and they're going to split by a value of 5 again. So in this case, we have a little bit of overlap. Therefore, we are going to draw this like small peak, big peak, small peak, small peak, big peak, small peak. And I tried to do that as pretty as possible. It didn't really work, but don't worry, I will redraw it for you. So this is going to look like... And if you really look at it, you can see that just like the doublet of doublets that we did, here we have a set of triplets. So we have 2 triplets, and we are going to call that a doublet of triplets. I'll erase this just to be clean. And as we can see, we did in fact get the same number. 6 is the number of peaks we have, and we would call that a doublet of triplets. So you must be wondering what kind of questions could he ask about complex splitting, and that's what we're going to do right now. So I've already gone ahead and drawn in the hydrogens and written out the hybridizations, and the hydrogen we're going to look at is the one in purple. And we're going to look at the splitting for that. As you can see, one side is sp2, one side is sp3 again, so we're going to use the n1 plus 1 times n2 plus 1 rule. I'm sorry if I said that kind of weird. And again, I've labeled just left from right, so this will be neighbor 1 and this will be neighbor 2. And we're going to write out, again, 1 neighbor plus 1 times, pay attention, 3 neighbors now, plus 1. So that will give us 2 times 4. That's 8. And just for the sake of practice, that would be a doublet of quartets. And that's pretty much it. The only other example that we're going to do for complex splitting is one that is like this, because most of the ones on your exam will either look like this or the one we just did. So for this kind of question, I want you to immediately see and highlight the word theoretically, and then JAB does not equal JBC. This is very important because when you actually look at HA, HB, and HC, you can see that they would actually, in reality, all be completely equal. And the reason for this is because there's no different hybridizations going on. Everything is normal. But he's saying theoretically, if they were different, what would the multiplicity be? So we're looking at hydrogen B, so the one I am highlighting. And we're going to find the theoretical splitting for that if JA did not equal JB. JAB did not equal JBC, excuse me. And so once again, I'm going to use the n1 plus 1 times n2 plus 1 rule. And I'm going to call A 1 and C 2. I only drew 3 of the hydrogens on A, but since we have these 2 methyl groups, that's going to be 6 plus 1. And then we have 2 hydrogens on position C, so we're going to have 2 plus 1. We get 7 times 3, which gives us 21. So the theoretical splitting would be E21.